All right, so today we're continuing our study of thermochemistry. On Friday, we talked about Hess's law, right, which is the way we can calculate the heat of reaction. We use Hess's law when we have several steps and we have a reaction that we're interested in. We manipulate those steps to figure out what the net reaction is, and then we add them up, right? So that's Hess's law. That's one way to calculate heat of reaction. The other method for calculating heat of reaction is called standard enthalpies of formation. So again, this is the reference page you can use during class and stuff. If you have a hard time reading the font, you can also bring your textbook and use it. Now, a note on these reference pages, depending on the textbook, the number of sig figs might vary ever so slightly. Okay, so the calculations that I did that we're going to go over today were all based on your textbook's reference table. The handout that I've given you, the last decimal place or two might vary ever so slightly. So just FYI, heads up about that. If you are using your textbook, these tables are at the very, very back. I have a nice little bookmark here. Thermo table, which begins in our textbook on page A26. It's at the back of your textbook, and it goes for several pages. Okay, so here's what it looks like if you're using your table. We are only interested in delta H right now. We'll deal with delta S and delta G next semester in Chem 2. So that's where these numbers are in your textbook. Like I said, you can also use the handout that I just gave you, but the font is really small. Okay, so we're talking standard. When we say standard, standard is just a reference place. Okay, so for instance, if you're measuring, I don't know, weight loss, right? You're in a fitness program. You start with your baseline, what's your weight, and after you do these new exercises or whatever, you can look at how much you've lost, or maybe if you're trying to bulk up, how much you've gained in reference to where you started, right? So standard state is just a reference state. Okay, it's just a reference point. And so for thermodynamics calculations, that's 1 atmosphere pressure. If it's a solution, it's a concentration of 1 molar, and it's 25 degrees Celsius. And we denote standard state by using this little degree sign, okay? So if you look, here we go. In your reference page, it has this little degree sign. Okay, that has nothing to do with temperature. That little degree sign, anytime you see that, means that it's reference. It's that standard state. Now, I want to make sure you understand the difference between standard state and STP, okay? Because standard state is what we use in thermodynamics calculations. All of the handout values are at standard state, okay? Now, that's not the same as STP, which is standard temperature and pressure, which deals with the gas phase. Okay? In a few weeks, we're going to talk about the gas phase. Actually, next week. It's not a few weeks. Next week, we'll deal with gas calculations, okay, and we'll talk about STP. That's not the same thing as standard state in a thermodynamics reference, okay? So just make sure you have in your mind, if you know what STP is from previous classes, it's not necessarily the same thing as standard state. And standard state is for thermo calculations. All right, so that little degree sign, it just means that you're under these conditions. And so heat of formation, that's what that little F stands for. The standard heat of formation is the heat change when 1 mole of a compound is formed from its elements in standard state. All right, so if you're looking at your handout, notice, let's just look at your handout together. Start at the beginning, aluminum, right? Al solid. Its delta H, that's the first column, is 0, right? Any pure element in its most stable form is going to have a delta H of 0, okay? So solid aluminum or oxygen gas or any element in its most stable form, okay, has a delta H of 0. Now notice that's not the same thing as Al3+, right? Forming Al3+ has a delta H of -531. Forming aluminum ion from aluminum metal, right? That's where you get that value from. If you go down, AlCl3, notice it's -705.6. So this is the heat change when you form 1 mole of AlCl3 from aluminum metal and chlorine gas, right? Okay, so that's what that's referring to. So the heat change when you have 1 mole of that compound formed from its elements under standard conditions. That's what we're looking at when we're looking at these tables. Okay? And like I said, for a element in its most stable form, it's 0. Now, I say most stable form because sometimes elements are listed in there in more than one state of matter. So if you go to cesium, there's a good example over here. There's cesium. There's cesium gas, there's cesium liquid, and there's cesium solid. Notice cesium solid is the only one that has delta H of 0, right? Because cesium solid is the most stable form. Okay? Cesium liquid has 2.087, and cesium gas is 76.5, right? So most stable form is the one that's got the 0. Does everybody understand how this table works? What it's telling us? Okay, like I said, this is not something that you would memorize. I will give you a table with heats of formation on it. I'm definitely not expecting you to memorize heats of formation. They're in your textbook at the back. They're also in this handout that I just gave you. So when you're doing these kinds of calculations, what are you calculating? What are you actually computing? You're computing the energy difference between the reactants and the products. Okay, it's really important that you understand the energy associated with breaking and forming bonds. Okay? It takes energy, it requires energy to break bonds. And then energy is released when bonds get formed. Okay? So for instance, where's my meter stick? If I want to break this, right? I want to break my meter stick, I have to apply effort, right? It takes energy to break bonds. And then we get that energy back when we form bonds, as we'll talk about in actually around week 13. We'll do we'll do a little bit of molecular orbital theory, we'll do a little bit of valence bond theory to help us understand why energy is released when bonds are formed. Okay? Because the basic premise of this is that when two molecular orbitals get close enough that they can overlap, that reduces energy. If molecular orbitals are overlapping in a positive way, that actually reduces the amount of energy required than if they're separate. Okay? And we'll get into that in greater detail when we talk about valence bond theory and MO theory a little bit. But make sure you understand the difference. Okay? It takes energy to break bonds. Energy is released when bonds are formed. Now, if you're thinking about biology, biologists actually talk about that backwards. Right? They talk about that in a different context. So make sure you understand the way chemists look at this versus the way biologists look at this is different. Okay? Because biologists are not looking at thermodynamics the same way a chemist is. Okay? So delta H is the energy released when bonds form. In other words, that's the products, right? It's always final minus initial. So the energy released when we form new bonds minus the energy we spent breaking up all the bonds of the reactants. Okay, does this make sense? You gotta break all the bonds of the reactants. That requires energy. And then you get energy back when you form new bonds. So the difference between that's delta H. And it's always final minus initial, right? Products minus reactants. Never the other way around, because then your calculation will be backwards. So again, this is in your appendices in your book. It's also on the handout I just gave you. So if this is our reaction, A, little B, little C, little D, those are just the coefficients, the balanced chemical equations coefficients, right? A, B, C, D. Then, if that's our generic reaction, delta H is the coefficient of C times its heat of formation plus the coefficient of D times its heat of formation, right? And these are coming from our reference page. We're going to add those together. Now, if there's a third one, right, you put it there as well. Minus the coefficient of A times its heat of formation plus the coefficient of B times its heat of formation. So if you're familiar with summation notation, that's what this is, right? It's the sum of the heat of formations times their coefficients of the products minus the sum of the heats of formations times their coefficients of the reactants. It always, 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 always is products minus reactants. Always. If you do it as reactants minus products, your answer will be backwards. Okay, it's products minus reactants. Because delta anything is always final minus initial. And in a reaction sense, the final state is the product, and the reactant state is the initial. Final minus initial. So the sum of the heats of formations of the products times their coefficients for the products minus the sum of the heats of formations of the reactants times their coefficients. So you always have to check your reaction and make sure it's balanced. right? Because if there's a coefficient of 4 here, you would multiply heat of formation of A times 4. Okay? If there's a coefficient of 2 here, you multiply heat of formation of B times 2. Add those together, and then add these together as well. And again, if there are more reactants than 2, more products than 2, you'd add those in there as well. Does this make sense? Does everyone understand what we're doing? Any questions on how we're doing this? So let's just do some examples. Oh, this is what I just said. Okay. So here is combustion of propane. Right? So we've got propane gas, oxygen gas as our reactants, producing carbon dioxide and water. Now, all these are coming from the table here. Now, these values might vary ever so slightly just because sig figs are based on the reference page you're looking at. Okay, so the textbook that you have in front of you is what I was using for these. Okay? So for CO2, it's a product, right? The coefficient is 3. So on my table, I find carbon dioxide, gas, right, because state of matter matters, 393.5, negative. So 3 times the heat of formation of CO2, which is right there, plus 4, because that's the coefficient, of H2O. Now, when you're writing combustion, you always write H2O as a gas, never as a liquid. Okay, because think about it. When you're watching a fire burn, are you seeing a little puddle form? No, right? It's water vapor that you're forming. So make sure you write H2O as a gas and not as a liquid. So if you find H2O, it's under hydrogen. H2O gas, negative 241.8. Yep, that's the same as what I have here. So we're going to add those together. And then from that, we will subtract. Coefficient of propane is 1. Let's see. Propane, negative 104.7. Oh, that textbook rounded it to 105. Okay, so again, it might vary based on your textbook. Coefficient of 1 there. And then how come this one is 0? That's a pure element in its most stable form, right? So O2, and if you want to confirm it to yourself, you could. Oxygen's on the back. O2 gas is 0. Okay? If there was O2 liquid, that would not be 0. It's a pure element in its most stable form. Now we just add those and then subtract. Okay, but does everyone understand where these numbers came from, how I obtained them? So now I just do some arithmetic. And I come up with negative 2,042.7 kilojoules. Delta H is negative. That means it's exothermic. So if I'm standing next to this reaction occurring, will I feel heat or will it feel cold? Will it feel hot or cold? Exothermic? It'll feel hot, right? Standing next to a fire, it feels hot, right? We were roasting marshmallows yesterday on my stick, right? It got hot. Stuck it a little bit too far in. Got too hot, right? If delta H is negative, that's exothermic, heat is being released. You would feel heat. Your beaker would get hot. If it's positive delta H, heat is being absorbed, right? Your beaker would get cold. So the process here is pretty straightforward, as long as you understand that A, it's products minus reactants, and B, don't forget to multiply by the mole ratios, right, the coefficients. And like I just said, if you're doing combustion, you always write H2O as a gas, not as a liquid. You're not forming liquid water in a combustion. Okay, so here's a picture representation of what we're doing here. Right? When we're doing this kind of problem, we are calculating the energy difference here. I've got to break all these bonds, right? I've got to break that carbon, hydrogen, that carbon, hydrogen, that carbon, hydrogen, that carbon, hydrogen. I've got to break all 4 of those. I've also got to break that double bond and that double bond, right? Break, 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 break. Got to break all those. And then these bonds form, and then these bonds form. And that's what I am doing. I'm breaking all these bonds, and I'm forming all these new ones. These require energy. These give me energy back. So I break those, form those, and that's what I'm calculating when I do this process. Okay, that's what I'm doing. So I'm going to answer negative 785. Would that be exothermic or endothermic? Exothermic, right? Would that feel hot or cold? What would it feel? Hot or cold? Hot, right? No, it works for any reaction. These are just the ones that I'm picking here. All right, so I want you to try this one. Calculate delta H for the combustion of ethanol. I've even given you the equation already. So I'll pause it. Let you try it. Let's see what we got. So we're looking up, again, your sig figs might vary on the heats of formation just because of difference in reference table used, but I don't think it's going to be a significant difference. I got negative 1,235.4. If you rounded that to 1,235, that's fine. And we're not going to get scrupulous about sig figs here because we're not calculating any of these values. We're not measuring any of these values ourselves. Right? We're just using the values from a reference table and we're crunching numbers. But we do need to have units, right? Units are going to be kilojoules. All of these are kilojoules, so make sure you do include units. Does a value of negative 1,200 make sense for combustion? Would you expect combustion to be largely exothermic? Yes, you would. Okay, why don't you try combustion of ethane, which is C2H6, and then calculate delta H for that one. Let's see what we have. Combustion, before you even pick up your calculator, you could predict. Would you expect it to be exothermic or endothermic? You would expect that to be exothermic. I got negative 2,858. Neighborhood, again, it's going to depend on number of sig figs that your reference table gives you, right? So if yours, for instance, is 1575.5, but in the grand scheme of things, that's not going to make a huge difference in your final answer. What is going to make a huge difference is if you don't have your equation balanced, right? If your equation is balanced incorrectly, that is going to make a huge difference. Coefficients are 2, 7, 4, 6. Another thing that will make a huge difference is if you forget to do products minus reactants and you do it as reactants minus products, right? Because a lot of students just think, oh, they read it left to right. They're going to do the reactants first because they come first when you read it. But you've got to remember delta means final minus initial. Final is over there, initial's over here. Those are the two things that get people in trouble. Not balancing the equation, products minus reactants. That's what you got to do. Okay, do this one. The thermite reaction occurs when aluminum metal reacts with solid iron 3 oxide to produce solid aluminum oxide and iron metal. What's the enthalpy change for this reaction? I'll let you think about that for a minute. Oops. All right. What kind of reaction is this? That would be single displacement, right? So there's the reaction, and it's delta H. That's what I got. Again, assuming my sig figs in my table are very, very analogous to yours. Did you get something very close? Again, your rounding might be slightly different based on the number of sig figs in your answer. If yours came out to be negative 851 or negative 850.3, that's not a major difference. If you came out with negative 2,000, that is a major difference. Two of them are 0 though, right? Iron metal and aluminum metal, both are 0. Pure elements in their most stable form. Do we agree on this one? We agree within rounding? All right, what about formation of this precipitate? Ag plus and Cl minus. There's the net ionic equation. Net ionic equation here, right? Forming a precipitate. So I came up with negative 65.7. Again, your answer might vary ever so slightly based on number of sig figs in your reference page versus mine. but it shouldn't be a major, major difference. Is anyone coming out with like major, huge differences? Because again, it's just going to vary based on the number. Every table carries different number of sig figs here, right? Some might call that negative 126.9, or negative 127.1, right? It's all going to vary based on the sig figs of your reference table. But what makes the difference is order, right? Products minus reactants and coefficients. Here are all the coefficients of 1. Okay, what about this one? Iron 3 oxide, otherwise known as rust, is formed from iron metal and oxygen gas. What's delta H for this reaction? All right, let's look at this one. We need to write a balanced equation first. Right, coefficients 4, 3, 2. But this one's nice and convenient for us because we've got 2 of them that are 0. Right? So all we have to do is look up Fe2O3 and multiply by 2. Do we agree? Agree within rounding based on how your table matches mine? So this one's nice and easy, right? Because when you've got zeros, it makes life easier. All right, last one. Combustion of methanol, CH3OH. Okay, this is the last one, and then we're going to talk about something else real quick. So there's the balanced equation, and I came out with negative 1276, 1277, depending on how you round it. Do we agree within rounding? These are all exothermic. They just happen to all be exothermic. Is it possible to have an endothermic? Of course, right? I just happen to pick all exothermic reactions. But if it were endothermic, what would be different? What would the sign be? Positive, right? Okay. So this is to find the overall change in enthalpy, right? So either Hess's law, which is what we did on Friday, or heats of formation, which we did today. Now, what if we want to know heat release for just one specific substance? We're not looking at the entire reaction, we're just looking at one particular substance. So this is the calculation you could do there. When 1 mole of methane is burned under constant pressure, 890 kilojoules of energy is released. What is delta H when a 5.8 gram sample is burned? Okay, so what we're going to do is we're going to use this piece of information right here as a conversion factor. Right? This is how much energy is released when 1 mole is burned. So if I've got 5.8 grams, how could I turn grams into kilojoules? What could I do? Convert to moles, right? And then I can multiply for every 1 mole that I burn, right? I get 890 kilojoules of heat. Right? So we convert grams to moles. Molar mass is 16.04. That's number of moles. And now, make sure you factor in that negative sign. The problem says it is released. If heat is released, does that mean delta H is positive or delta H is negative? Delta H is negative, right? So make sure you read the problem correctly. If it said it was absorbed, what would the sign here be? Positive, right? So make sure you read the question really carefully. Heat released versus heat absorbed, right? If heat's released, you would have a negative here. If heat's absorbed, you would have a positive here. So delta H for this process would be negative 320 kilojoules, which makes sense, right? Combustion would have a negative delta H. Does everyone understand how to do this one? I'm pretty sure there's one like this on your homework set too. Thing to watch there is the sign. That's the big thing to watch. Okay, here's one for you to do. Decomposition of 1 mole of solid calcium carbonate requires 556 kilojoules of heat. Calculate delta H when 24 grams is decomposed. Constant pressure just means you're not under some non-standard conditions, right? That's all that means. Okay, last problem. Let's look at the solution here. So we know that the mass is 24 grams. we know that this process requires 556 kilojoules. So is the sign, when we do our calculation, going to be positive or negative? Positive, right. This is energy that we are requiring. That means that that's energy that needs to go in. So this is a positive value right here, right? This is positive 556. This is energy going in. This is not energy being released. So this is endothermic, right? You have to add energy to the system for this to happen. So I got 133 kilojoules. Or if you round it to 2 sig figs, which is what you technically should do because we've got a mass of 24 grams, that'd be 130. Everybody good on this? Just a second, I'm going to stop the recording and then I will. Yes.